Chemical reactions in aqueous solutions are among the most important classes of chemical reactions. They include precipitation reactions, acid-base reactions, and redox reactions, all of which we consider in some detail in subsequent videos. For now, we have to remind ourselves what solutions are and look into some of the properties of aqueous solutions, including two of the most important types of solutes, electrolytes and non-electrolytes. So a solution is a homogeneous mixture of two or more substances. There's only one visible phase present, and the mixture is uniform throughout, meaning a subsample taken from the mixture would be representative of the whole. Solutions are comprised of the solvent, which is the substance present in the greatest amount, and the solutes, which are all other substances present. The solutes are said to be dissolved in the solvent. Aqueous solutions are homogeneous mixtures where water is the solvent, and we'd be very familiar with, for example, dissolving sodium chloride, table salt, into water to form an aqueous solution. Here's a representation of that process. We've got solid sodium chloride salt crystals being added to water to form the aqueous solution where the sodium chloride is dissolved in water. Now, aqueous solutions are so important in chemistry that they're given their own subscript, this AQ subscript, and that designates that that particular solute or that particular substance is dissolved in water. I probably should stress at this stage that dissolving of a solute in a solvent is a physical process. There's no new substances formed, so it's not a chemical process. It's actually just a straight physical process. You can have many different types of aqueous solutions. We can have solids dissolved in water, such as salt dissolved in water in seawater, or caffeine dissolved in water, solid caffeine dissolved in water in our cup of coffee. We can have liquids dissolved in liquid water as well. For example, acetic acid is the main component of vinegar, and acetic acid is a liquid at room temperature and pressure. And alcoholic beverages have the liquid ethanol dissolved in water. We can also have gases dissolved in water to form aqueous solutions. For example, oxygen dissolved in water to allow fish and other marine organisms to respire. It turns out that many aqueous solutions conduct electricity, and solutes that result in a conducting solution when they are dissolved in water are called electrolytes. And it turns out that the electrical conductivity of these solutions is actually due to the presence of dissolved ions, that's positively charged cations and negatively charged anions, which are able to move and migrate in the presence of an electric field. So here again we have that representation of the dissolving of solid salt in water to form the aqueous sodium chloride solution. It's probably better represented, however, this aqueous representation here as dissolved sodium ions freely floating around, solvated sodium ions with their own AQ subscript, and freely mobile chloride ions floating around in solution. So water is able to do something quite unique. It's able to break apart the positively charged sodium ions, which are attracted to the negatively charged chloride ions. They're able to break apart that physical attraction so that we have separate sodium ions, solvated sodium ions in solution, and separate chloride ions in solution. We can represent this pictorially as well. Here's a two-dimensional representation of the crystal lattice of sodium chloride with alternating positively charged sodium ions and negatively charged chloride ions. When we add water to this crystalline structure, what actually happens is those positively charged bits and negatively charged bits become physically separated. They become solvated and surrounded by water molecules, and in effect we've got freely mobile sodium cations and freely mobile chloride anions floating around in solution. So If I were to take that solution and stick a pair of electrodes in there and hook those electrodes up to a voltage source such as a battery, we could actually see where the source of this electrical conductivity comes from. So this is a completed electric circuit. In the electric circuit, in the external circuit, the electricity is carried by the charge carriers, electrons, in the copper wire. So in the external circuit, the charge carriers are electrons going through the electrodes and the copper wire. In solution, however, what we've got is the charge is actually being carried by these positively charged cations and the negatively charged anions. And what we see is that the positively charged cations, the sodium ions, migrate towards the negatively charged cathode in the presence of an electric field. We also see that the negatively charged anions migrate towards the positively charged anode. And this phenomena occurs due to the attraction of opposite charges. So the positively charged anode attracting the negatively charged chloride ions, the negatively charged cathode attracting the positively charged sodium ions. And so whilst we've got the mobile charge carriers being electrons in the external circuit, in the solution the electrical charge is being carried by these mobile ions, positively charged and negatively charged, sodium and chloride ions. So it turns out that any soluble ionic compound will dissolve in water to form freely mobile ions and will form electrolytes. It's fairly obvious, therefore, that any insoluble compounds, compounds that do not dissolve in water, are non-electrolytes. They're not going to produce the freely mobile anions and cations that are responsible for carrying the charge in electrical circuits. You may think that anything that dissolves in water produces an electrically conducting solution, but that's not the case. Not all soluble compounds are electrolytes, and in fact we have many molecular compounds, and here's an example here that you'd be familiar with, the dissolving of sugar. Sugar is comprised of the molecule sucrose, C12H22O11, and again we can see a representation there where solid sucrose is placed into water and transformed into aqueous sucrose. So what we've got here is the aqueous subscript representing the fact that this compound is now dissolved as an aqueous solution in water. It does not break apart to form ions. There are no ions in the sucrose molecule. It's a substance that dissolves in water to produce a non-conducting or poorly conducting solution, and we term those substances non-electrolytes. Now you may think that all molecular compounds, because they don't contain ions, are going to be non-electrolytes, but that's not true either. There are molecular electrolytes, and not all electrolytes are ionic compounds. And the most important class of compounds that are molecular electrolytes include the acids, for example, hydrochloric acid, hydrofluoric acid, hydroiodic acid, hydrobravic acid, nitric acid, sulfuric acid, acetic acid, etc. Here's an example here where we have the molecular compound hydrogen chloride. It's a gas at room temperature and pressure. If it's bubbled through a water solution, that hydrogen chloride gas will dissolve in water to form HClAq, which means that we've got this compound hydrogen chloride now dissolved in water. What actually happens when it dissolves in water, however, is the water molecule is able to break apart the hydrogen chloride molecule into freely mobile hydrogen ions, H plus ions, and freely mobile chloride ions, Cl minus ions. And so the molecular compound hydrogen chloride being dissolved in water actually produces ions in solution, and those ions can carry an electrical current. And so what we've got here is an example of a molecular electrolyte, and the acids being the most important class of those molecular electrolytes. We can classify electrolytes into strong electrolytes or weak electrolytes. Strong electrolytes are substances that exist almost exclusively as ions in solution, and we've seen a couple of examples of that already, where the compound dissociates completely to form ions, and sodium chloride is an example of that. We've got sodium chloride solid being dissolved in water to form the aqueous solution, but that aqueous solution is probably best represented as separate sodium ions and separate chloride ions. And again, the hydrogen chloride example, the molecular electrolyte, hydrogen chloride gas being bubbled through water to form the solution, but that solution being best represented as separate H plus ions and separate Cl minus ions. And so this reaction is complete in one direction, going from left to right, and the substances here existing almost exclusively as ions in solution. They dissociate completely to form these freely mobile ions. That's quite different to weak electrolytes, in which are substances that ionize only slightly upon being dissolved in water. And examples here include weak acids such as acetic acid and weak bases such as ammonia, and we deal a lot with weak acids and weak bases later on in this video course. Here's an example of acetic acid. Its formal name is ethanoic acid. It's a molecular compound. This molecular compound, when it's dissolved in water, is able to be broken apart to form the hydrogen ion and the acetate ion, or the ethanoate ion. The unique feature of this particular chemical equation is the presence of these double arrows, an arrow going to the right as well as an arrow going to the left. And what that actually means is that this process here is significant in both directions. So in other words, as the acetic acid molecule is dissociating to form the hydrogen ion and the acetate ion at the same time, the acetate ion and the hydrogen ion are recombining to form the molecule, the acetic acid molecule there. And so you've got a process here that's appreciable in both directions. This process is actually called an equilibrium process, technically a dynamic equilibrium process, because it is dynamic. It's dynamic in the forward direction as well as dynamic in the reverse direction. And this substance here is not completely dissociated at any point in time into separate ions, and so we would call this a weak electrolyte because it's only slightly ionized upon dissolution. We deal with weak electrolytes, weak acids, weak bases later on in the course.